Another substitution method is the Bernoulli method. Let's talk again about how we've gone so far about solving differential equations. We've talked about separable equations when we can get the y's and the x's on opposite sides of the equal sign. We've talked about linear equations that can be put in a particular form. And then we learned a substitution method. It was the homogeneous substitution method, which put with a simple transformation of v equals y over x, we were able to get the equation into a separable form. The next substitution method, the Bernoulli sub, this is going to be able to take another particular form of a differential equation and put it into, this time not a separable form, but a linear form. The form of the type of differential equation that can be solved with Bernoulli is in this form. So it's very similar to the linear form. However, that y to the n multiplying the qx makes it decidedly not linear. So we're going to do a substitution method that's going to make this actually into linear form. That is simply v equals y to the 1 minus n power, where n is the exponent of the y that's multiplying the qx term. I think the best way of explaining this type of substitution is to just use an actual example. So I've got one here. If you match this equation to my general form, you can see that n is equal to 3. That means that v is going to be y to the 1 minus 3 power, or v is equal to y to the negative 2 power. As we did with the homogeneous substitution, I'm going to go ahead and take the derivative of the substitution, and I'm going to get that dv dx is simply equal to negative 2y to the negative 3 power times dy dx. I'm going to go about doing this a little differently than some textbooks do, because I find that doing it this way helps us catch errors more than other methods. So what I'm going to do first is that everywhere I see the dy dx, I'm going to replace it with my new value for dy dx. So first let's take this substitution and solve for dy dx. That's my first step, and my second step simplifies the exponent. And this is what I'm going to use to substitute into my actual differential equation. So what I've done differently here that I didn't do when I was going through the homogeneous substitution is I right now have v's and y's and x's. I will at my last step get rid of the y's, but what I want to do now is divide both sides by whatever's in front of my dv dx. I want to get this in standard form. And this is what I get when I divide both sides by negative 1/2 y to the 3rd power. It's at this point I see the y I have exactly equals the very substitution I wanted to make. That is v equals y to the negative 2 power. If at this step you are not able to get rid of all your y's, then you've set the problem up incorrectly. Because now what I have is an equation completely in linear form. That is, it's in the form of this, but instead of y's I have v's. Now I can go ahead and solve it using the integration factor. Let's go ahead and do that. I find that mu of x is equal to the integral e to the 10 dx, which is equal to e to the 10x, and then I'll go ahead and solve. This is my general form, and then I'll go ahead and substitute in the mu of x that I've just calculated, and now I'll go ahead and integrate both sides with respect to x. As always, the left-hand side, the integral of a derivative is just equal to what the integrand is, but the right-hand side I'm going to have to do integration by parts. And when I go ahead and do that, I get it down to this form, and now I'll do my last integration. Alright, so now what I need to do is divide both sides out by that e to the 10x, so I get v by itself, and this is what I get my v down to. And remember, although we can roll constants together, the e to the negative 10x is not a constant, so we have to leave the c out front. We can't just replace that with another constant. Of course, this is in terms of v, not y, so let's go ahead and resubstitute. Since v is equal to y to the negative 2 power, I get that y to the negative 2 power is equal to everything I have on the right-hand side. And in this case, I'm going to leave it in implicit form. Let's do one more example. Here's my second example. I'm going to use prime notation in this case, just to give us a chance to see both Leibniz form and prime notation. In this case, n is equal to 1/3, which means v is going to be equal to y to the 1 minus n power, or in this case, the 2/3 power. And like before, we'll take the derivative of both sides of our substitution, and then we'll solve for dy dx. And we'll go ahead and substitute this back into our differential equation. But before I do that, I'll go ahead and put it in prime notation rather than Leibniz notation. On exams, I don't care if you use prime notation or Leibniz notation, your questions will have them in both forms. Let's go ahead and put this in standard linear form, that is, divide out both sides by 3/2 y to the 1/3 power. Now, as before, the only y is exactly what my substitution was originally, that y to the 2/3 power, so I'm going to go ahead and substitute that in with the v. And now we have a completely linear equation that we already know how to solve. So let's go ahead and do that, starting with the integration factor. When we find the integration factor, we can't leave it in this form. This is why I wanted you to recall your logarithmic property rules. We can rewrite that natural log as the natural log of x to the -2. And now the exponent of a natural log just leads us to x to the -2 power. And that's what we're going to use for our mu of x. Here's the general way I set up a linear equation. And now I'm going to go ahead and substitute the mu of x that I've just calculated. Once I have it in this form, I can go ahead and integrate both sides with respect to x, like I've done in the past, and my left-hand side is x to the -2 power times v, and then my right-hand side works out to be 2/9 x to the 3rd plus c. As before, I'll divide both sides by x to the -2, and my last step, whenever I'm doing this Bernoulli substitution, is to get it back in terms of y. So in this case, v is equal to y to the 2/3 power. And again, I'm going to leave my answer this time in an implicit form.